Now, just very quickly to go through the answers to the questions that I gave you in the workbook the last day, to make sure that you understand exactly what's going on in terms of chemical equilibrium. And I think these questions do sum up what we need to know about the first lesson in chemical equilibrium that we will have studied on yesterday. Okay, 70.18. A swimmer swims upstream at the same speed as the water moving in the opposite direction. Is this static or dynamic equilibrium? Now, the key thing to remember about two words, static and dynamic. Static means stopped. Static means no movement. So there's a swimmer swimming and there's water moving. That's obviously dynamic equilibrium, okay? It's the same thing that happens to you when you walk up the wrong side of an escalator in the shops, yeah? You walk up the escalator coming down. If you walk up at the same speed that it's coming down, you're not going to get anywhere. So the escalator's coming down, you're moving up, that's dynamic equilibrium. Likewise, running on a treadmill. If you're running on a treadmill, you're running at a speed forward that matches the speed of the actual tread on the mill coming backwards. So therefore, both of you are moving, nobody's getting anywhere. That's dynamic equilibrium. Part B. What do you mean by saying that a system has reached a state of equilibrium? And when we say it's reached a state of equilibrium, what we mean is that there appears to be no further decrease in the concentration of reactants and no further increase in the concentration of products, even though we know that the system contains contains a reversible reaction. Explain the term dynamic equilibrium, part C. Dynamic equilibrium is a state of balance. Now that's extremely important, okay? So dynamic equilibrium is a state of balance achieved when the rate of the forward reaction is the same as the rate of the backward reaction in a closed system. Part D. Give one example of a reversible reaction. Now, the easiest one to remember in terms of a reversible reaction, so you don't have to be scratching your head, is litmus paper. If you take red litmus paper and dip it into a base, it goes blue. If you take that out and dip it into an acid, it goes red. Back into the base, it goes blue. Back into the acid, it goes red. So you can change the colour of the litmus paper quite easily. That's a reversible reaction. It's an easily reversible reaction. So think of an indicator. That's probably the easiest way. Litmus paper would be your best one. Give one example of an irreversible reaction. Well, the one thing we all hate, rust on the car. You scratch the car, the oxygen gets in, the water gets in, the iron begins to chemically react with both, and we get corrosion, which we call rust. And you cannot turn rust back into iron, so it's irreversible. State Le Chatelier's principle. Now, Le Chatelier's principle states that when a system in dynamic equilibrium experiences a stress, the position of equilibrium will be altered in order to cancel the stress. That's it. And we've gone through a couple of examples already. I'm no doubt we're going to go through a few again here now. Part G. Dinitrogen tetroxide, which is a gas at temperatures above 294, dissociates according to the equation. Now that's important. So it's a gas above 294. So when it hits 294, it dissociates. That means at temperatures above 294, it breaks up. Meaning, the higher the temperature, the more towards the right-hand side that this is going to go. I hope that makes sense to you. Okay, so if we're moving this way, I hope you can see a little arrow, it's up there. If we're moving this way, so from left to right, that's what it says. At temperatures above that, it dissociates. So the dinitrogen tetroxide, this guy here, dissociates at temperatures above 294. So obviously, the higher the temperature, the more dissociation is going to take place. That's my little pen acting up there. So what would you see happening if the temperature of the sample N2O4 were raised from 295 to 330? Well, obviously, it would move equilibrium towards the right-hand side, and that sample would get dark brown. It would go browner. The brown colour would darken as you increase the temperature. Okay, part H. For the equilibrium system, 2 sulfur dioxides plus oxygen sets up dynamic equilibrium with 2 sulfur trioxides. Predict the effect on the equilibrium system of, now, removing SO3. So first of all, there are 3 stresses: pressure, temperature, concentration. Okay, pressure is only a stress when all species in my system are gaseous. Okay, temperature is a stress on every reversible reaction, as is concentration. Now, if you're removing SO3, what you're doing is you're decreasing the amount of SO3 available. So that's the stress you're putting on the system. Okay. In order to counter that stress, the system wants to produce more. It wants to replace what you've taken out, meaning that the position of equilibrium will move to the right-hand side over here. And what about adding more O2? Well, again, if you add more O2, you're increasing the concentration of O2. That's a stress. What will the system do? Try to decrease the concentration of O2 by getting it used up. And in this system here, it'll move away from the O2 again towards the SO3. So by removing SO3 and adding O2, you're driving equilibrium in both situations towards the right-hand side. Part I. Hydrogen and iodine react together to form hydrogen iodide as follows. It was found that changing the pressure, now be careful, pressure has no effect on the position of equilibrium here, okay? Pressure is only a stress when all species are in the gaseous form. That's number one. And we notice here, 1, 2, 3. So they are all in gaseous form, but it still has no effect. And that's the second reason I gave you yesterday. Look at both sides. There is 1 volume of hydrogen plus 1 volume of iodine. So that's 2 volumes on the left-hand side. There are also 2 volumes of hydrogen iodide on the right-hand side, meaning that the left and the right-hand side have the same number of volumes. So therefore, there's no smaller side to go to when you increase the pressure, and there's no larger side to go to when you decrease the pressure. So here's a second very important lesson. If pressure is a stress and all species are in the gaseous form, it will only have an effect on the position of equilibrium if the number of volumes left and right of the equation are different. Okay, so in this case here, the number of volumes are the same, so no effect. Part J, draw a graph to illustrate the setting up of the equilibrium reaction N2 plus 3H2 exists in dynamic equilibrium with 2NH3, and label the axis time and the y-axis concentration. Okay, let's see if we can do that. Just give me a moment here until I find my whiteboard. It takes a moment. Okay. I'm going to switch between the two here now, so just bear with me. Let's not heat up there for a moment. So what are we told to do? We're told to label the x-axis as time and the y-axis as concentration. And then we're reacting N2 and 3H2 with 2NH3. So we're starting off at N2 and H2, ending up at NH3. Okay. Now, oh, look at that. That was from last year. Isn't that incredible? Let's try and blank the whole thing if I can. Can I? Clear the canvas. Hooray. Okay, so let's see now if we can work this out. So, if I take the x and the y axis, now forgive my handwriting because I'm doing this on the screen, and we're told, if I can remember, that the x-axis is time and the y-axis is concentration. Okay, now what are we starting off with? We're starting off with N2 and H2. So both of those will be starting off at high concentrations. H2, N2. Okay, and we're producing ammonia. So we're producing NH3. And that means we're starting off at a low concentration of NH3. In fact, we're probably starting off with nothing. But anyway, the graph is the most important thing. Over time, what happens? Well, obviously, these two start to decrease, like so. That. And this one here starts to increase. And what we see happening is, because it does exist in a state of dynamic equilibrium after a while, is that they'll all flatline. They'll all come down to, oops, sorry, forgive my diagram, but they'll all come down to exactly the same flat line. So here is where we can say the system has reached a position of dynamic equilibrium. See that? So that's the dynamic equilibrium. So you're starting off with high concentrations of H2 and N2. As they react, their concentrations will drop. And as the NH3 is produced, down here, the ammonia, its concentrations will rise. And because the system comes into dynamic equilibrium, and we know that by the two arrows pointing either way, we will get a situation in time where there will appear to be no further increase or decrease in any of the concentrations. And at that point, we say that the system has reached a position of dynamic equilibrium. Now, I hope that diagram helped you. Okay, next page. There we go. Oh, next page. Part K. The production of ammonia from nitrogen and hydrogen is usually carried out at a pressure of around 200 atmospheres and a temperature of 450. The equation for that is N2 plus 3H2 exists in the dynamic equilibrium with 2NH3. Explain why high pressures lead to an increased yield of ammonia. Now, high pressures. First of all, pressure is only a stress if all the species are in the gaseous form, and they are in this case. Okay. Also, pressure will move the position of equilibrium as long as there's an imbalance between the number of volumes on the left hand side and right hand side. Well, 3 and 1, there's 4 volumes over here, there's 2 volumes over there. So why does high pressure lead to an increased yield of ammonia? Because when you increase the pressure on the system, the equilibrium will move to the smaller side, which is the ammonia. It will favour the production of ammonia. Okay. Why are very high pressures, e.g. 1,000 atmospheres, not normally used? Now, can you imagine the amount of money you'd have to spend to reinforce the container that would try to hold 1,000 atmospheres? Imagine the money involved. Companies not willing to do that, so therefore they compromise at about 200 atmospheres. Part L. What would the influence of increasing pressure and increasing temperature on the condition of equilibrium be in the following exothermic reaction? Now that's nice that they tell us that, because we do need to know what the forward reaction is. It's exothermic. Okay, so if the forward reaction is exothermic, the backward one is endothermic, and you can keep that in your minds. So first of all, pressure. Increasing pressure. Increasing pressure pushes the equilibrium towards the smaller side, the ammonia side. So therefore that is going to be increased in concentration because of an increase of pressure. What about increasing the temperature? Now think, if I increase the temperature, that's my stress. The system tries to bring the temperature down, and the only way that the system can bring the temperature down is by favouring an endothermic reaction, which we said at the beginning was the backward one. So if I increase the temperature, the equilibrium is going to move towards the left hand side and favour the presence of N2 and H2. Okay. Part M. Comment briefly on the industrial importance of the above reaction and state the conditions in which it's usually carried out. Now, if you notice, this is the first stage of what we call the contact process. We bring sulfur dioxide together with oxygen to form sulfur trioxide, and then we allow the sulfur trioxide to mix with water to form the sulfuric acid. But in this case here, state the conditions. Well, look, let's talk about pressure first of all. Pressure will favour the smaller side. So if I want to have a good, decent amount of SO3, I'm going to have to increase the pressure. But again, high pressures are not usually used in industry. And for the contact process, which is most unusual, the pressure used is just over 1 atmosphere. Just over 1 atmosphere. And temperature, well, the forward reaction is exothermic. That means that we have to drop the temperature to keep it going towards the right hand side. But low temperatures also make reactions sluggish. They decrease the rate of reaction. So that means that we have to again compromise on a pressure of just over 1 atmosphere and a temperature of roughly 450 to 500 degrees. Okay, 17.2. A gas X decomposes to form a mixture of 2 gases Y and Z. The forward reaction is exothermic. The following equilibrium is set up. How will the yield of Y and Z be affected by an increase in pressure? Well, increase in pressure pushes equilibrium towards the smaller side. So if I increase the pressure, equilibrium moves towards X. So the concentration of X will increase. What about an increase in temperature? Well, it tells me the forward reaction is exothermic. So if I increase the temperature, the system will try to decrease the temperature by favouring the endothermic reaction, which again drives equilibrium towards the left-hand side. 17.3. In the case of each of the following reactions, what would the effect on the dissociation of A, increasing the pressure, and B, increasing the temperature? Okay, let's take pressure first of all in the first one. All in gaseous form, yes. 2 volumes on the left, 2 volumes on the right-hand side. Pressure has no effect whatsoever. What about the second one in terms of pressure? Pressure, there's 2 volumes here and there are 4 volumes here, and all species are in the gaseous form. So pressure will cause the equilibrium to move to the smaller side when it's increased, and that means it will favour the production of ammonia. What about increasing the temperature? Well, if I increase the temperature, that means I favour the endothermic reaction. And what we're told here is that the forward reaction is exothermic. So that means if I increase the temperature on this one, the equilibrium move again towards nitrogen monoxide. It'll move towards the left. And down here, be careful, the forward reaction is already endothermic, okay, because it's taking in heat. So the forward reaction is endothermic, and that's the reaction that's favored by increasing temperatures. So if I increase the temperature in the second one, the equilibrium will move towards the right hand side, over here. Okay, now that's it. I haven't done anything in relation to 17.4 because that's actually a demonstration I need to show you in school. We will have time after the, well, I'm saying mocks tentatively, after the mocks we'll have time to demonstrate this thing again and revise. But for the moment I'm just interested in the fact that you understand how the position of equilibrium can be altered by any one of the three stresses: concentration, temperature or pressure.